Okay, so what we're going to consider now, having had a broad overview of the theory and some of the models in sequence stratigraphy, and then a practical thinking about time relationships within strata. Let's think about some of the complications and some of the reasons why those models may not be so straightforward to apply. So just as a reminder, sequence stratigraphy is a tool for interpreting time relationships and a tool which allows us to correlate a map between different regions where we have data, and sort of a series of models based on that tool which allow us to or guide our interpretations in areas where we don't have much data. Okay, so typically, particularly when we look at seismic data, we interpret the sort of patterns we associate with sequences a number of different scales, spatial scales. So essentially we might identify a number of relatively small sequences that stack into a number of relatively big sequences. And this has been sort of placed formally into this idea of the order of a sequence. So again, if you look in the literature, you'll find that often people refer to third order or fourth order sequences when they're interpreting sequences in seismic data. They might refer to fourth order and fifth order when they're working mainly with outcrops or well data. So the idea is, fifth order that's the smallest scale of sequence which is typically interpreted. Fifth order sequences have relatively short durations, a few 100,000 years, for example, and they stack into bigger sequences of fourth order. Fourth order stack into bigger sequences of third order stack into even bigger of second order, and then you know where this is going, second order stack into first order. So just to say a little bit about that, first order cycles, we're thinking about hundreds of millions of years. So really, the accumulation of supercontinents and their breaking up. So really first order tectonic cycles. Second order cycles in the order of tens of millions of years, and they reflect changes in seafloor spreading rates. So when a seafloor spreads rapidly, the mid-ocean ridges at the base, or constructive plate margins, oceanic plate margins, have a large volume, and that means that global sea level is high as a result. When seafloors are spreading more slowly, mid-ocean ridges have smaller volumes, and then global sea level is correspondingly lower. Third order cycles, well, typically there we're thinking about several million years. So these are typically the scale that we might interpret on seismic reflection data. And there can be a number of drivers. We can think about increases in the volume of ice in polar ice caps, and what that means for locking up seawater in those ice caps. So typically when ice caps grow, that means that sea level falls as a result because the water is taken up into the ice cap. When the ice caps melt, we release that water and global sea level rises. So that's what we mean by glacioceustacy. The glacio bit refers to the ice cap, and eustacy basically means global sea level. We can also geoidal eustacy here. This refers to the distribution of oceans and continents around the globe and what that means for gravity acting on the Earth's surface. So again, this can cause typically relatively small variations in global sea level on this scale of millions of years. And we can also think about tectonic processes, again, operating in this sort of several million year sort of time frame. Fourth order cycles, typically we're thinking about less than a million years, and fifth order cycles, we're thinking about even shorter periods, hundreds of thousands of years. And once we start to look at those timescales, which are relatively small in tectonic terms, we typically think about glacioceustacy. So this is back to the ice caps, and how those ice caps are growing and shrinking in response to Milankovitch climate cycles. And there are three well-defined orders of Milankovitch climate cycle. There's 20,000 years, 100,000 years, and 400,000 years. And typically this is the sort of conceptual framework we use to interpret those relatively high frequency changes in accommodation space that we see, particularly if we can trace them out over large areas and demonstrate that they're maybe not global, but at least they act regionally. Okay, so typically small sequences stack into bigger sequences, and we have a number of different mechanisms that we can refer to as potential controls. However, it's not so simple. I mean, so here's a list of controls, and these are really parameters that control accommodation space or sediment supply. We can have eustatic sea level, global sea level, subsidence. Now that might be something that varies between basins or within a basin. That could be tectonic subsidence, or it can be compaction. If we deposit lots of sediment quickly, that sediment compacts, and that also causes subsidence. Sediment supply, and there are a number of drivers there. That can be, uplift of the hinterland, releasing clastic sediment. It can be climate and how that controls weathering of that sediment in the hinterland. It can be how fast or how slowly it takes that sediment from the drainage basin, the hinterland, to actually reach somewhere where we deposit it in the basin. And if we're thinking about carbonate and evaporite sediments, well, they grow or are precipitated in place within the basin. So there's different aspects of sediment supply. Bathymetry, antecedent bathymetry, that means the bathymetry which is inherited from an older phase of the basin history. So an example there would be if we have a basin with a shelf, a slope, a basin floor geometry. We've already seen that we expect that the stratal architectures that we produce to be different from a basin with a ramp geometry with just a smooth, simple gradient. We also have the internal behavior within the depositional systems and their kind of linked, their sort of linked source to sink systems between them. One example there is delta lobes shifting position. It's an example we'll come back to tomorrow when we think about shallow marine systems. But increasingly, we're recognizing there are feedbacks in between, within depositional systems that control where sediment is deposited and stored. And the bottom line is, this is already a long list, but there are different feedbacks between the processes and those mechanisms. So in practice, what that means is it's often not straightforward at all to work out what the driving mechanism is for a particular feature that we can observe and document. Again, I would say keep it simple, stick to sediment supply and accommodation space. This list of controls really relates to, controls on those two parameters. Okay, so graphically, this is a way of showing a little bit more about those controls. So upstream controls, that could include tectonic uplift and climate, how I release sediment. Sort of midstream controls, that really determines how long it takes the sediment to travel from this hinterland in towards the basin where it's deposited. That could be a long, tortuous route, as this diagram is showing here, or if the hinterland is right next to the basin, there could be that release of sediment could take place very quickly. Once we get into the basin itself, we can think about eustacy and subsidence as being important. So this is just a kind of a cartoon representation of some of the controls I've just talked through. Of course, this diagram shows a relatively simple configuration of a depositional system, transport network behind it, and hinterland up here. We know that there are many basins we see on the Earth's surface today that don't look like this. So here's a model for a rift basin with active faults. Those faults are associated with erosion of the fault block crests, and you see these little drainage basins in here. And then they feed depositional systems just next to the drainage basin, so not a very long transport distance. But we also have some larger rivers shown through here, which are cutting across or traveling around these fault blocks and potentially feeding sediment from outside the basin to the interior of the basin. And of course, there are places here where we have lakes localized in extent, places where we have, coastal plain deposits, rivers, and so on. So what we see in here, in 3 dimensions, a very complex arrangement of where we have accommodation space being generated in the hanging wall of these faults. And at the same time, we have uplift and erosion in the footwall of those faults. That varies as we go from the center of the faults towards the tips of the faults. And of course, sediment is being steered around those faults if it's coming in from outside the basin, or it's being locally produced at the crests of those fault blocks. So in this kind of setting, a tectonically active setting, complex in 3 dimensions, we haven't even considered how this might change through time, but again, we could imagine extra complexity. It would not be appropriate to apply the simple models that we talked about earlier. We'd have to think things through from first principles, again, thinking about accommodation space and sediment supply, where those two are present and how they might interact with each other. So not so simple just to take a model off the shelf and apply it without thinking through very carefully how we might do that. Okay, so in practical terms, I realize I've probably given you quite a discouraging message. How on earth can we apply these models? Well, if we want to work out the controls on sediment supply and accommodation, there are a couple of things we can do. So one, when we're mapping things out, we can try to work out the lateral extent of features. That might be the lateral extent of an unconformity at a sequence boundary, for example, or it could be of a maximum flooding surface or some of the units within a basin fill. And the extent to which we can trace things out tells us, if we can only trace things out locally, that implies maybe there's just a local control. If we can trace them out over a whole basin, that implies we need to think of a control which operates on the scale of the whole basin. We can also think about the timing and duration of these different features. Are they present? If we need good age data here, so that would mean probably high resolution biostratigraphic data. But can we demonstrate with those data that certain features are forming at the same time across the basin, or do we see evidence of them forming at different times across a basin? That can also help us to unravel these different controls. And the third point here is if we see patterns being repeated, so cyclical patterns, that implies that the mechanism we infer as a control must be repeating again. It must be acting in a cyclical manner again and again and again. The one note of caution here, though, is that actually, in a strict sense, demonstrating cyclicity probably requires, well, we can have most confidence in that if we apply some statistics to the patterns that we're seeing, and those patterns meet the statistical requirements to demonstrate this cyclical arrangement. So those are a few things that we can do. The other thing I would say is increasingly there's numerical and physical modeling tools which allow us to sort of test the simple models that I showed earlier. They're probably not quite in the mainstream yet. They may not be things you've come across at your undergraduate degrees, for example, but increasingly it's possible to carry out numerical modeling experiments or experiments in flume tanks which allow us to get insights to these different potential controls. That can also be helpful in allowing us to constrain uncertainty. We can run multiple different models and we get a sense about how different or how similar the results are. And that again helps us to constrain uncertainty as we fill in space in areas, in our interpretations in areas that lack data. And we can also use objective descriptions. So the system structure we talked through, for example, the fact we say that they are high stand or low stand, we're automatically tying those to parts of a sea level curve. And that can be quite dangerous in a strict scientific sense. It's far better if we separate description from interpretation. So description, well, we could refer to regression or transgression, aggradation, progradation. That's descriptive. The shoreline is building out, it's retreating, it's stacking vertically. We're not saying anything about the sea level curve in that sense. So just a few slides in here. So numerical modeling tools, in this case, a numerical model of a shelf, a slope, a basin floor, and we can control the inputs to those numerical models in terms of sediment supply, sea level changes, etc. I'm not going to talk through any of those in any detail, but just to point out that those tools are available and they do allow us to test interpretations with some rigor. We can also think about physical models. So those are flume tanks, again, where we control some of these parameters and we observe the patterns that are produced. So here's a model of a flume tank, and we'll be interpreting data from an experiment in a flume tank later this afternoon. And here's a cross section, a little bit like a seismic line from landward to basinward through a flume tank, a few meters in width and length. And you can see stratal patterns in here that we can relate to the controls that we have input into those models. The second thing about objective ways of describing stratigraphy, and that there's two different approaches here which I think are valid. So one is to trace out breaks in slope, so either at the shoreline or at the shelf edge. Those are specific features in the morphology of a basin, and we can trace how those have moved through time. So we can describe the trajectory of those boundaries as they move. And we can do that using seismic data, for example, where we have the geometrical information to pick out those boundaries. Or, for example, a shoreline might be associated with a particular type of facies that we can map out using outcrop or well and core data, for example. And we can say, does that trajectory, is it building outwards? Is it building upwards? Is it retreating? So we can use shoreline and shelf edge trajectories in that as one way of objectively describing the patterns that we see. A similar approach using, so this was sort of proposed by Exxon a little bit over 10 years ago, was a way of refining some of the models they first proposed, is to use progradation versus aggradation. So progradation with the black arrows here, aggradation with the green arrows, transgression with the arrows with the transparent heads, and sort of downstepping by these red downward pointing arrows. And again, you can see in here they've picked particular features either because they have a geometrical aspect which is easy to recognize, or because they might be distinctive facies in wells, cores, outcrops, and we can trace those positions. And again, we can say something about how much they've built up vertically, or they've downstepped vertically, and how much they've moved towards the basin, how much they've moved towards the basin margins. So again, aggradation, progradation, transgression or retrogradation, those are terms we can use without having to assign these rather interpretive system strats. Okay, so I'm going to stop there, but we'll be coming back to these ideas in a practical at the beginning of the next session.